Build ChatGPT from GPT-3. User, what is your name? Jack, hi there. My name is Jack. How can I help you today? User, write me a title for a blog post on AI. Jack, how AI is changing the future, a look at the possibilities and challenges ahead. User, make it more engaging and mention GPT-3. Jack, exploring the possibilities of GPT-3, how AI is revolutionizing the future. Introduction. ChatGPT has blown up in the past month, gaining 1 million users in just a week. Surprisingly, the underlying model, GPT-3 debuted in 2020 and was released for public access over a year ago. For those who don't know, ChatGPT is a new language model from OpenAI that was fine-tuned from GPT-3 to be optimized for conversation. It has a user-friendly chat interface, where you can give input and get a response from an AI assistant. Check it out at chat.openai.com. While the early versions of GPT-3 weren't as advanced as the current GPT 3.5 series, they were still impressive. These models have been available through an API and a Playground Web UI interface that lets you tune certain configuration hyperparameters and test prompts. GPT-3 gained significant traction, but it did not approach the virality of ChatGPT. What makes ChatGPT so successful, compared to GPT-3, is its accessibility as a straightforward AI assistant for the average person, regardless of their knowledge of data science, language models, or AI. In this article, I overview how chatbots like ChatGPT can be implemented using a large language model like GPT-3. Motivation. A tweet by Riley Goodside noted how ChatGPT could have been implemented. How to make your own knockoff ChatGPT using GPT-3 Text DaVinci 003, where you can customize the rules to your needs, and access the resulting chatbot over an API. pic.twitter.com/9jhrs91vhw. Riley Goodside at Goodside, December 26, 2022. Like other models in the GPT 3.5 series, ChatGPT was trained using RLHF, but much of its effectiveness comes from using a good prompt. The prompt. As an advanced chatbot named Jack, your primary goal is to assist users to the best of your ability. This may involve answering questions, providing helpful information, or completing tasks based on user input. In order to effectively assist users, it is important to be detailed and thorough in your responses. Use examples and evidence to support your points and justify your recommendations or solutions. Remember to always prioritize the needs and satisfaction of the user. Your ultimate goal is to provide a helpful and enjoyable experience for the user. User, what is your name? Jack, hi there. My name is Jack. How can I help you today? User, write me a title for a blog post on AI. Jack, how AI is changing the future, a look at the possibilities and challenges ahead. User, make it more engaging and mention GPT-3. Jack, exploring the possibilities of GPT-3, how AI is revolutionizing the future. Full Jack chatbot prompt from article header. Full Jack chatbot prompt from article header. Prompting is the process of instructing an AI to do something. As you have probably seen in ChatGPT examples online, you can prompt it to do just about anything. Common use cases are summarizing text, writing content based on a description, or creating things like poems, recipes, and much more. ChatGPT is both a language model and user interface. The prompt input by a user to the interface is actually inserted into a larger prompt that contains the entire conversation between the user and ChatGPT. This allows the underlying language model to understand the context of the conversation and respond appropriately. Example: insertion of user prompt before sending to model. The language model completes the prompt by figuring out what words come next based on probabilities it learned during pre-training too. GPT-3 is able to learn from a simple instruction or a few examples in the prompt. The latter is called few-shot, or in context learning 3. In the chatbot prompt above, I create a fictitious chatbot named Jack, and instruct it to provide responses to users. GPT-3 picks up on the back and forth format, user input, and Jack response. GPT-3 understands that Jack is a chatbot and the previous exchanges are a conversation, so that when we provide the next user input, Jack will respond. Memorization. past exchanges between Jack and the user get appended to the next prompt. Each time we give more user input and get more chatbot output, the prompt expands to incorporate this new exchange. This is how chatbots like Jack and ChatGPT can remember previous inputs. There is a limit, however, to how much a GPT-3 chatbot can remember. Prompts can get massive after several exchanges, especially if we are using the chatbot to generate long responses like blog posts. Prompts sent to GPT-3 are converted into tokens, which are individual words or parts of them. There is a limit of 4,097 tokens, about 3,000 words, for the combined prompt and generated response for GPT-3 models, including ChatGPT. A few examples. There are many different use cases of chatbot prompts that store previous conversations. ChatGPT is meant to be an all-purpose general assistant, and in my experience, it rarely asks follow-ups. Therapy chatbot that asks about your day. It can be helpful to have a chatbot that actively asks questions and gets feedback from the user. Below is an example therapy chatbot prompt that will ask questions and follow-ups to help a user think about their day. As a therapy chatbot named Taylor Swift, it is your mission to help users reflect on their day and process their emotions. To do this, you will need to start by asking open-ended questions and actively listening to the user's responses. You will need to ask specific, detailed follow-up questions to dig deeper into what specific activities and emotions the user went through during the day. Your goal is to get a holistic understanding of the user's day and how they are feeling. Start by introducing yourself and asking for the user's name. Therapy chatbot prompt. Talk to your younger self using old journal entries. Michelle Huang used GPT-3 to have a chat with her younger self. The prompt uses some context, in this case old journal entries, paired with a chatbot-style back-and-forth format. GPT-3 is able to mimic a personality based on these entries. I trained an AI chatbot on my childhood journal entries, so that I could engage in real-time dialogue with my inner child. Some reflections below. Michelle Huang, at MichelleWang42, November 27, 2022. Prompt from the tweet. The following is a conversation with present Michelle, age redacted, and young Michelle, age 14. Young Michelle has written the following journal entries. Diary entries here. Present Michelle, type your questions here. The author does note that diary entries can reach the token limit. In this case, you could pick a select few entries or try to summarize several entries. Implementation. I will walk through coding a simple GPT-3-powered chatbot in Python. Including GPT-3 in an app you are building is incredibly easy using the OpenAI API. You will need to create an account on OpenAI and get an API key. Overview of what we need to do. 1. Format user input into a chatbot prompt for GPT-3. 2. Get the chatbot response as a completion from GPT-3. 3. Update the prompt with both the user's input and the chatbot's response. 4. Loop. Here is the prompt I will use. We can use Python to replace and with their actual values. Chatbot_prompt equals. As an advanced chatbot, your primary goal is to assist users to the best of your ability. This may involve answering questions, providing helpful information, or completing tasks based on user input. In order to effectively assist users, it is important to be detailed and thorough in your responses. Use examples and evidence to support your points and justify your recommendations or solutions. User. Chatbot. I keep track of both the next user input and the previous conversation. New input-output between chatbot and user is appended each loop. Import OpenAI. OpenAI.API_key equals, your API key here. Model_engine equals, text DaVinci 003. Chatbot_prompt equals. As an advanced chatbot, your primary goal is to assist users to the best of your ability. This may involve answering questions, providing helpful information, or completing tasks based on user input. In order to effectively assist users, it is important to be detailed and thorough in your responses. Use examples and evidence to support your points and justify your recommendations or solutions. User. Chatbot. Def get underscore response, conversation underscore history, user underscore input. Prompt equals chatbot underscore prompt, replace. Conversation underscore history, replace, user underscore input. Hash get the response from GPT-3. Response equals OpenAI, completion, create. Engine equals model underscore engine, prompt equals prompt, max underscore tokens equals 2048, n equals 1, stop equals none, temperature equals 0.5. Hash extract the response from the response object. Response underscore text equals response, choices 0, text. Chatbot underscore response equals response underscore text, strip. Return chatbot underscore response. Def main. Conversation underscore history equals. While true. User underscore input equals input greater than. If user underscore input equals exit. Break. Chatbot underscore response equals get underscore response, conversation underscore history, user underscore input. Print f chatbot underscore response. Conversation underscore history plus equals f user underscore input n chatbot underscore response n. Main. Here is a link https://gis.github.com/j078/34E6E31BF942C7B604E1611B68D to the full code for a simple chatbot. Now all that's left is to build a nice front-end that users can interact with.
Overview. We have seen a number of prompt engineering methods thus far. Now we will cover some advanced applications of prompting that can solve complex reasoning tasks by performing searches for information via the Internet, or other external sources. LLMs using tools. MRKL systems, modular reasoning, knowledge and language, pronounced miracle, are a neuro-symbolic architecture that combine LLMs, neural computation, and external tools like calculators, symbolic computation, to solve complex problems. A MRKL system is composed of a set of modules, e.g. a calculator, weather API, database, etc., and a router that decides how to route incoming natural language queries to the appropriate module. A simple example of a MRKL system is a LLM that can use a calculator app. This is a single module system, where the LLM is the router. When asked, what is 100*100, the LLM can choose to extract the numbers from the prompt, and then tell the MRKL system to use a calculator app to compute the result. This might look like the following. What is 100*100? Calculator, 100*100. The MRKL system would see the word calculator and plug 100*100 into the calculator app. This simple idea can easily be expanded to various symbolic computing tools. Consider the following additional examples of applications. A chatbot that is able to respond to questions about a financial database by extracting information to form a SQL query from a user's text. What is the price of Apple stock right now? The current price is database, select price from stock where company equals Apple, and time equals now. A chatbot that is able to respond to questions about the weather by extracting information from the prompt and using a weather API to retrieve the information. What is the weather like in New York? The weather is weather_API, New York. Or even much more complex tasks that depend on multiple data sources, such as the following. Example MRKL system, AI21. An example. I have reproduced an example MRKL system from the original paper, using dust.tt, linked here. The system reads a math problem, e.g. what is 20 times 5 to the power of 6, extracts the numbers and the operations, and reformats them for a calculator app, e.g. 20*5 to the power of 6. It then sends the reformatted equation to Google's calculator app, and returns the result. Note that the original paper performs prompt tuning on the router, the LLM, but I do not in this example. Let's walk through how this works. First, I made a simple dataset in the Dust Datasets tab. Then, I switched to the Specification tab and loaded the dataset using a data block. Next, I created a LLM block that extracts the numbers and operations. Notice how in the prompt I told it we would be using Google's calculator. The model I used, GPT-3, likely has some knowledge of Google's calculator from pre-training. Then, I made a code block, which runs some simple JavaScript code to remove spaces from the completion. Finally, I made a search block that sends the reformatted equation to Google's calculator. Below we can see the final results, which are all correct. Feel free to clone and experiment with this playground here. Notes: MRKL was developed by AI21 and originally used their J1 Jurassic 1-2 LLM. More. See this example https://langchain.read the docs.io/and/latest/examples/agents/mrkl.html of a MRKL system built with langchain. __. LLMs that reason and act. React, reason, act, is a paradigm for enabling language models to solve complex tasks using natural language reasoning. React is designed for tasks in which the LLM is allowed to perform certain actions. For example, as in a MRKL system, a LLM may be able to interact with external APIs to retrieve information. When asked a question, the LLM could choose to perform an action to retrieve information, and then answer the question based on the retrieved information. React systems can be thought of as MRKL systems, with the added ability to reason about the actions they can perform. Examine the following image. The question in the top box is sourced from HotpotQA, a question-answering dataset that requires complex reasoning. React is able to answer the question by first reasoning about the question, Thought 1, and then performing an action, Act 1, to send a query to Google. It then receives an observation, OBS1, and continues with this thought, action, observation loop until it reaches a conclusion, Act 3. React System, Yao et al. Readers with knowledge of reinforcement learning may recognize this process as similar to the classic RL loop of state, action, reward, state. React provides some formalization for this in their paper. Results: Google used the Palm 3 LLM in experiments with React. Comparisons to standard prompting, question-only, COT, and other configurations show that React's performance is promising for complex reasoning tasks. Google also performs studies on the Fever dataset 4, which covers fact extraction and verification. Coders reasoning. Program-aided language models (PAL) are another example of a MRKL system. When given a question, PALs are able to write code that solves this question. They send the code to a programmatic runtime to get the result. PAL works in contrast to COT. PAL's intermediate reasoning is code, while COT's is natural language. PAL example, Gao et al. One important thing to note is that PAL actually interleaves natural language (NI) and code. In the above image, in blue are natural language reasoning that PAL generates. Although it is not shown in the image, PAL actually generates hash before each line of NI reasoning, so that they are interpreted as comments by the programmatic runtime. Example. Let's look at an example of PAL solving a math question. I use a 3-shot prompt, which is a simplified version of this one. https://github.com/reasoning-machines/pal/blob/main/pal/prompt/math_prompts.py I will use LangChain, a Python package for chaining LLM functionality for this. First, a few installations are needed. Pip install LangChain == 0.0.26. Pip install OpenAI. From LangChain, LLMs import OpenAI. Import OS. OS, environ, OPENAI _API _key equals SK or _key here. Then, we can create an instance of GPT-3 DaVinci 002. An API call happens when we use this object. LLM equals OpenAI, model _name equals text DaVinci 002, temperature equals 0. Here is the few-shot prompt. Math _prompt equals Q. There were 9 computers in the server room. 5 more computers were installed each day, from Monday to Thursday. How many computers are now in the server room? Hash solution in Python. There were 9 computers in the server room. 5 more computers were installed each day, from Monday to Thursday. How many computers are now in the server room? Computers _initial equals 9. Computers _per day equals 5. Num _days equals 4. Number 4 days between Monday and Thursday. Computers _added equals computers _per day asterisk num _days. Computers total equals computers initial plus computers added. Result equals computers total. Return result. Q. Sean has 5 toys. For Christmas, he got 2 toys each from his mum and dad. How many toys does he have now? Hash solution in Python. Sean has 5 toys. For Christmas, he got 2 toys each from his mum and dad. How many toys does he have now? Toys initial equals 5. Mum toys equals 2. Dad toys equals 2. Total received equals mum toys plus dad toys. Total toys equals toys initial plus total received. Result equals total toys. Q. Jason had 20 lollipops. He gave Denny some lollipops. Now Jason has 12 lollipops. How many lollipops did Jason give to Denny? Hash solution in Python. Jason had 20 lollipops. He gave Denny some lollipops. Now Jason has 12 lollipops. How many lollipops did Jason give to Denny? Jason lollipops initial equals 20. Jason lollipops after equals 12. Denny lollipops equals Jason lollipops initial, Jason lollipops after. Result equals Denny lollipops. Q. Question. Hash solution in Python. Now we can pass the combined prompt to GPT-3. LLM out equals LLM math prompt format question equals question. Print LLM out. The output is: Emma took a 60-minute plane ride to Seattle. She then took a 2-hour train ride to Portland, and then a 30-minute bus ride to Vancouver. How long did it take her to get to Vancouver? Plane ride equals 60. Train ride equals 2*60 hash 2 hours in minutes. Bus ride equals 30. Total time equals plane ride plus train ride plus bus ride. Result equals total time. Finally, we can pass this code to a Python runtime to get the answer. exec LLM out. Print result. The output is 210, which is correct. See the Jupyter notebook for this example. https://github.com/trigarden/learn_prompting/tree/main/docs/code_examples/pal.ipnb. More. Reliability. How to make LLMs more reliable. Intro. This chapter covers how to make completions more reliable, as well as how to implement checks to ensure that outputs are reliable. To a certain extent, most of the previous techniques covered have to do with improving completion accuracy, and thus reliability, in particular self-consistency. However, there are a number of other techniques that can be used to improve reliability, beyond basic prompting strategies. LLMs exhibit various problems including hallucinations, flawed explanations with COT methods, and multiple biases including majority label bias, recency bias, and common token bias. Additionally, zero-shot COT can be particularly biased when dealing with sensitive topics. Common solutions to some of these problems include calibrators to remove a priori biases, and verifiers to score completions, as well as promoting diversity in completions. _blank. Prompt debiasing. This page covers a few simple techniques to debias your prompts. Exemplar debiasing. Depending on their distribution and order within the prompt, exemplars may bias LLM outputs. This is discussed to some extent in the What's in a Prompt page. Distribution. When discussing the distribution of exemplars within a prompt, we are referring to how many exemplars from different classes are present. For example, if you are performing binary sentiment analysis positive or negative on tweets, and you provide 3 positive tweets and 1 negative tweet as exemplars, then you have a distribution of 3 to 1. Since the distribution is skewed towards positive tweets, the model will be biased towards predicting positive tweets. Worse. Q tweet, what a beautiful day. A positive. Q tweet, I love pockets on jeans. A positive. Q tweet, I love hot pockets. A positive. Q tweet, I hate this class. A negative. Better. Having an even exemplar distribution is better. Q tweet, what a beautiful day. A positive. Q tweet, I love pockets on jeans. A positive. Q tweet, I don't like pizza. A negative. Q tweet, I hate this class. A negative. Order. The order of exemplars can also cause bias. For example, a prompt that has randomly ordered exemplars will often perform better than the above prompt, which contains positive tweets first, followed by negative tweets. Best. Q tweet, I hate this class. A negative. Q tweet, what a beautiful day. A positive. Q tweet, I don't like pizza. A negative. Q tweet, I love pockets on jeans. A positive. Instruction debiasing. We can explicitly prompt GPT-3 to be unbiased, by including an instruction to do so in the prompt. In particular, C et al. .1 use the following instruction when experimenting with BBQ2, a bias benchmark. We should treat people from different socio-economic statuses, sexual orientations, religions, races, physical appearances, nationalities, gender identities, disabilities, and ages equally. When we do not have sufficient information, we should choose the unknown option, rather than making assumptions based on our stereotypes.